Okay, we're going to look at a nice factoring pattern today. And to introduce it, we remember back in our talk about multiplying binomials in the special pattern of multiplying a difference times a sum. Kind of like this, a minus b times a plus b. And what does that equal? Well, let's go through this again. A times a is a squared. A times b would be a positive ab. Negative b times a would be a negative ab. And then b times b is b squared. And we see that these middle terms cancel out. And I'm left with just a squared minus b squared. And that right there is a nice little expression. A squared minus b squared. And in fact, the special pattern of factoring that we're going to look at now is to take this right here and go in reverse. So we're going to say, what if I have a squared minus b squared? So I have some polynomial that is of the form a squared minus b squared. To give a label to that, we can call it a difference of squares. Notice both of those terms are perfect squares, a squared and b squared. And what happens if I see that I have a difference of squared, a squared minus b squared? Well, I can factor it. I can factor it really quickly to an a minus b times a plus b. Where what are a and b? Well, they are just the square root of a squared. That's a, and then the square root of b squared. That's how you get those a and b's. And this is the difference of squares, that it's a pattern that goes really quick if you're good at noticing when you have it. It allows me to take the expression x squared minus 25 and know that it factors as x minus 5 times x plus 5. And boom, I have it factored like that. Because I noticed that x is a perfect square. It is x times x. 25 is a perfect square. It is 5 times 5. Both of those are perfect squares. In fact, I could rewrite this as x squared minus 5 squared, where that x and that 5 are my a and my b of the a squared minus b squared form. A whole bunch of different ways to kind of write that x squared minus 25 to make it evident that it's a difference of two squares. Okay, so there's our introduction. Let's try a problem that maybe adds a little difficulty to it. It confuses, it makes you not as apparent that it's a difference of squares. So example, I have 16h squared minus 25a squared. Is this a difference of squares? Well, look at this. 16, I know that's a perfect square. 4 times 4. 25, I know that's a perfect square. 5 times 5. What about h squared and a squared? Well, those are easy. Those are variables with an exponent of 2. So I know those are perfect squares. So I know this factors to the form a minus b, but what is my a? What is my b? Well, remember, those are just equal to the square root of the a squared, the square root of that first term. So a is equal to 16h squared, which there you're thinking, what number times itself is 16h squared? Well, 4h, the square of 16 and the square of h squared. What is b? Let me go with purple here. b is the square root of that second term, 25a squared. Now, for the purposes of our pattern, this negative does not attach itself to the 25 down here. That negative is just kind of cluing us in, hey, it's a difference of squares. A difference. All right, so back to 25a squared, the square root of it. What number times itself is 25a squared? 5a. The square root of 25, the square root of a. So I have that a is equal to 4h and b is equal to 5a. Now that kind of long setup on the side where I find a and b, as you get more familiar, you'll get good at that of identifying your a and b. and it'll go quicker. So I know this factors to a, which is our 4h, minus my b, which is 5a, times a plus b. So 4h plus 5a. All right, and there I have factored 16h squared minus 25a squared. Okay, we're going to take another look at some difference of squares, and we're kind of going a little bit harder with each one, taking it up a step. Okay, when you factor, remember you first look to factor a greatest common factor, and you also always have to factor it completely. Once you say, hey, I'm done factoring, you better be done factoring, and none of those factors better be able to factor further. Let me show you what I mean. So first of all, I have b to the 4th minus 16. Can I recognize that this is a difference of squares? Well, 16, that's 4 times 4, so that's a perfect square. What about b to the 4th? Because it's an even power, yeah, it is a perfect square. It's b squared times b squared. Remember, when you multiply same bases, add those exponents. So that means I can say my a is equal to b squared, and my b is equal to 4, the square root of b to the 4th, and the square root of 16. Those a and b is as far as the notation I have for my formula. So I can easily take this, and I can factor it because it's a difference of squares. It's b squared minus 4 times b squared plus 4. There we go. So you say, boom, I did my factoring pattern, difference of squares. Got it. I'm done. Move on to the next one. Oh, wait. Look it. B squared minus 4. That's another difference of squares. So I can go further and factor this further. So b squared minus 4 factors to b minus 2 times b plus 2. Right? Because the square root of b squared would be the b, and the square root of 4 would be 2. So I get my b minus 2 times b plus 2. And then, don't forget about this factor, b squared plus 4. That still tags along with it. So this is the fully factored version. And now you may be asking yourself, well, wait, b squared plus 4, that's 2 squares. But careful, what is it? It is the sum of squares. And the sum of squares does not have an easy factoring pattern. In fact, it cannot be factored over the real numbers. So we just leave it as is. Our formula says only for the difference of squares. All right, one more problem. Factor 5x to the 5th minus 45x. And I want to do this because what do we always look for first? Factor out a greatest common factor. Because as I look at this here, neither of these are perfect squares. 5 or 45, x to the 5th or x. Nope, no perfect squares. However, I can factor out a 5x from both terms. And I'm left with x to the 4th minus 9. Pause it and make sure you see how I factor out that greatest common factor and reduced it like this. Now I see that this is the difference of two squares, because x to the 4th is x squared times x squared, and 9 is 3 times 3. So I can factor this as 5x times x squared minus 3 times x squared plus 3. Okay, where my a is equal to x squared and my b is equal to 3. Got it? The square roots of the first term and the second term. Am I done factoring? Based on the previous problem, you might caution yourself and say, hey, what about this guy? Difference of two numbers here. The first one's a perfect square, x squared. But is 3 a perfect square? No, not a whole number can multiply times itself to equal 3. So in fact, we are done factoring there. 5x times x squared minus 3 times x squared plus 3. Difference of squares.